Today we'll be talking about analog to digital and digital to analog converter architectures. And it's Patrick Wang.
And Francesca Faerman.
To start off with, digital signal processing is the mathematical manipulation of an information signal used to modify or improve it in some way. It is characterized by the representation of discrete time, discrete frequency, or other discrete domain signals by a sequence of numbers or symbols and the processing of these signals. Digital signal processing and analog signal processing are subfields of signal processing. DSP includes subfields like audio and speech signal processing, sonar and radar signal processing, sensor array processing, spectral estimation, statistical signal processing, digital image processing, signal processing for communications, control of systems, biomedical signal processing, seismic data processing, etc. The goal of DSP is usually to measure, filter, and/or compress continuous real-world analog signals. Digital signal processing methods fundamentally require that an analog signal is quantized at discrete time instances and digitally represented as a sequence of words consisting of ones and zeros. To describe the DSP system, we should take a brief overview of the diagram in Figure 5.1. The diagram starts by taking in an analog signal source and passing it through a sample and hold circuit to create a discrete time model representation of the original source. This newly modeled signal is then put through an analog to digital converter circuit, which converts the mapped signal points to a digitally coded signal for interpretation. At this point, the digital signal is sent through a series of desired DSP filters and algorithms, and a new further manipulated signal is outputted. This would then consist of the final stage of the DSP system, where the user will decide whether to take the newly digitally interpreted analog signal and either continue to pass it through additional signal filters and use it completely in digital form, or convert the digital signal back to analog through a digital to analog filter. This completes the basic model for a DSP system, and the following slides will describe some of the fundamental A to D and D to A converter terminology, as well as help in exploring samples of common converter architectures.
Next, I will explain the fundamentals of A to D and D to A conversion. Analog signals can be given as either a voltage signal or a current signal, depending on the signal source. The output of an A to D converter is an n-bit digital code given by equation 5.1, where A sig is the analog signal, Fs is the analog full-scale level, and B sub n is a digital value of 0 or 1. Therefore, an n-bit D to A converter transfer equation would be given as in equation 5.2, where A sig is the analog output signal, and the digital code becomes the input. The resolution of a converter is the smallest distinct change that can be produced at an analog input or output for an A to D or D to A converter, and is expressed by equation 5.3. Delta A sig is the smallest reproducible analog signal for an n-bit converter. The relative accuracy of a converter is the worst-case error between the actual and ideal converter output after gain and offset errors are removed. The conversion rate is the rate at which a digital code or analog signal can be accurately converted into an analog signal or digital code respectively. Accuracy and conversion rate are therefore closely linked. Choosing a converter architecture is dependent on the conversion rate. Sensitive analog operations can either be done in parallel at the expense of accuracy or cyclically reused to allow high accuracy with lower conversion speeds. However, actual A to D and D to A converters exhibit deviations from the ideal response. Converter architectures and design trade-offs depend on fabrication process and device types. Parameters such as voltage threshold, physical dimensions, vary among semiconductors, and these variations can manifest themselves into errors. The first of these errors is the offset error, as can be seen in Figure 5.3. The difference between the ideal response and the actual response is an upward shift on the y-axis. This type of error can be removed by various trimming techniques at the expense of the conversion rate. Another type of error is the gain error, as shown in Figure 5.4. It can be defined as an error in slope of the actual response and can also be removed by trimming techniques. Integral nonlinearity is any worst-case deviation from an ideal drawn between 0 and the full-scale analog signal and cannot be removed by trimming. Figure 5.5 is an example of monotonic nonlinearity. Monotonicity in a converter means that the output will, at least, increase with increasing input. Certain converter architectures can guarantee monotonicity for specified numbers of bits of resolution. Non-monotonic nonlinearity can be seen in Figure 5.6, where increasing input does not guarantee increasing output. Settling time for D to A converters is the time taken from a change of the digital code to the point at which the analog output settles within some tolerance around the final value. Glitches may also occur during changes in the output at major transitions such as 1 MSB or half MSB. During large changes, switching time delays between internal signal paths can cause a spike in the output. The weight of these errors is heavily dependent on the choice of converter architecture. Data converters are often designed for low-cost implementation in standard digital processes that lack well-controlled resistors or capacitors. Absolute values of these devices can vary by as much as plus or minus 20%. Post-fabrication trimming techniques can be used, but at the expense of added cost and complexity to the manufacturing process. Various architectures can be used to allow high-speed or high-accuracy data conversion.
To reiterate, a digital-to-analog converter, also known as a DAC, decodes a digital word into a discrete analog level which can either be current or voltage-based, depending on the application. To describe the D to A converter architecture, let's take a look at the diagram in Figure 5.7. Glancing at the block diagram, an analog signal reference is taken in and attached to an analog scaling network, which routes the analog signal to a set of binary switches. These switches have been latched with the word value of the digital signal, and the resulting signal is applied to an output driver for the final stage processing. At this point, the output signal is now in analog form. The basic analog scaling network used in the D to A converter can be based on one of the following three scaling schemes: voltage scaling, current scaling, or charge scaling. In terms of voltage scaling, a serial string of identical resistors are placed between a reference voltage source and ground. Switches are then utilized to grab voltages off of the resistors and apply them to the output driver. For current scaling, switches are used instead to grab current through switch-scaled current sources. Finally, for charge scaling, a reference voltage is applied to a capacitor driver using scaled capacitors where the total capacitance value is determined by the digital code. Figuring out which D to A converter architecture to employ typically depends on a varied combination of the available components in the target technology, the desired conversion rate, and the required output resolution. Next, we will discuss some analog to digital converter architectures and some of their pros and cons. The highest speed architecture for analog to digital conversion is flash A to D, also known as parallel A to D. This converter architecture utilizes maximum parallelism for increased speed at the expense of output signal accuracy. The way that this architecture works is that it takes in 2 to the n minus 1 reference voltages and applies it to the negative input of the appropriate analog comparator. The original analog signal voltage is then applied to the positive input of each of the 2 to the n minus 1 analog comparators, and a resulting thermometer code is read from the output of the comparators. This resulting thermometer reading is further manipulated and converted to a digital word by a specified encoding logic. The overall speed of the converter is held in check by the time delay through the comparators and the chosen encoding logic scheme. If a high-resolution digital output signal is required, then this is not the appropriate A to D converter to utilize. In order to achieve even an acceptable performance result in terms of resolution, the reference voltage sent to each analog comparator must be precisely spaced out one least significant bit apart.
A successive approximation A to D converter is formed via a feedback loop around a D to A converter. Figure 5.9 shows an 8-bit successive approximation A to D. The successive approximation register, or SAR, is initialized to a value where all bits are set to 0 except the MSB, which is set to 1. This is the mid-level value. An analog signal is applied to the sample and hold, or SNH circuit. On the first clock cycle, the DAC converts the digital codes stored in the SAR to an analog signal. A comparator is used to determine whether the analog signal is greater or less than the mid-level value, and the control logic determines whether to leave the MSB set to 1 or to change it to 0. The process is then repeated on the next cycle, but the next MSB is tested. For an n-bit converter, n clock cycles are required to fully quantize each SNH signal. The speed and resolution of this converter is also limited by the speed of the DAC and any time delay through the comparator. Therefore, this type of converter architecture is widely used for medium speed and medium accuracy applications.
In contrast to flash A to D, the pipelined analog to digital converter allows for high resolution output conversion without the need for many comparators. The processing time of this converter architecture is held in check by the number of required conversions and the time delay through each stage. A pipeline A to D converter is referenced in the diagram in Figure 5.10. In this diagram, a partial conversion is performed and the converted bits are shifted down the pipeline through digital registers. Each pipeline stage adds an additional cycle of latency before the final code is converted. However, for multiple analog conversions, the initial overhead for the first conversion becomes minimal with each successive conversion. An advantage of utilizing a pipelined converter is that they allow for digital correction schemes to eliminate or reduce errors generated in the analog circuitry. Digital correction can also be achieved by employing higher resolution ADC and DAC circuits in each stage so that errors in the preceding stages can be detected and corrected digitally prior to the final output stage. Although there are even more analog to digital converter architectures out there in use today, you must narrow down which one to utilize by the type of speed and resolution constraints of the required system. And that's our presentation. We hope you enjoyed it.